Hi everyone. Problem 54 of Chapter 4 is a challenging problem which requires an understanding of mathematical concepts such as e and natural logarithms. For some of you, this problem goes beyond your current math abilities, but for others of you, this problem may have been a challenge you enjoyed working through. The problem states, use the Haldane map function to calculate the corrected map distance in cases where the measured recombination frequencies are 5%, 10%, 20%, 30%, and 40%. Sketch a graph of recombination frequency against corrected map distance and use it to answer the question, when should one use a map function? The Haldane map function is recombination frequency equals 1/2 times 1 minus e to the negative m, where e is a mathematical constant that is approximately 2.7, and m is the map correction. We are given the recombination frequencies and need to solve for m, so we need to manipulate this equation so that we are solving for m instead of the recombination frequency. A key concept in math that is important to remember here is that you can add components to equations as long as you do it to both sides, and it will not change the answer to the equation. This can aid you in solving for a different variable. I'd first like to get rid of the fraction on the right, so I'm going to multiply both sides by 2. 2 times 1/2 is equal to 1, so I can cross those out, and now we have 2 times the recombination frequency equals 1 minus e to the negative m. Next, I'm going to add e to the negative m to both sides of the equation, which is going to result in the subtracted e to the negative m being canceled out on the right side. Now we have 2 times the recombination frequency plus e to the negative m equals 1. Here you need to remember or use Google to learn that you can solve for e exponents by using the natural logarithm. The natural log rules state that the natural log of e to the x power equals the natural log of y, and that we can solve for x by multiplying the natural log of e. In this equation, x equals negative m and y equals 1 minus 2 times the recombination frequency. So we can convert our equation into negative m times the natural log of e equals the natural log of 1 minus 2 times the recombination frequency. Believe it or not, this new equation is very solvable. My first step here is to get rid of the negative in front of m, so I'm going to multiply both sides by negative 1. Next, I'm going to let you in on another secret. The natural log of e without an exponent is equal to 1, so I can just cross that out because m times 1 is m. Now I finally have the equation I can work with. M equals the negative natural log of 1 minus 2 times the recombination frequency. Recall that the problem wanted you to solve for recombination frequencies of 5%, 10%, 20%, 30%, and 40%. So, let's solve for the recombination frequency of 5%. Let's convert this percentage into a decimal, and the equation is now m equals the negative natural log of 1 minus 2 times 0.05. 2 times 0.05 is equal to 0.10, And 1 minus 0.10 equals 0.90. So m equals the negative natural log of 0.90. If I plug that into my calculator, I get negative 0.105, which multiplied by a negative equals 0.105. But I have 4 more of these to go, and then I need to do a graph, so I'm going to make it easy on myself and use a spreadsheet. If I make a column of my recombination frequencies, then I can plug the equation into my spreadsheet, and presto, we get the m for all the recombination frequencies. The final step to get the corrected map distance is you multiply m by 50%. Using this, I can create a graph in Excel or in Google Sheets, and we see that the corrected map distances are very close to the observed map distances when the map distances are small, but as the map distances get bigger, the corrections get bigger. For those of you who attempted this problem, I hope you enjoyed it.